Okay, this is the second video for 26201, alternating current, and we're talking about phase relationship of waves, sine waves. So here are two sine waves, and you can notice that they start at 0 at the same time, and they peak at the same time, and then they fall back to 0 at the same time. They reverse polarity at the same time, and they peak and they fall to 0. So these two waveforms are said to be in phase, meaning they're happening at the same time. If you put an AC voltage and current through a purely resistive circuit, the voltage and the current will be in phase. And we'll say that this is the voltage, and we'll say that this is the current. Now, here's the thing. When we look at this vectorially, you'll see that the current and the voltage are both on the 0 x-axis because they're in phase. They start at the same time and they have no degree of displacement between them, so they are in phase. However, if I have two waveforms where one of them is leading the other, and in this case, the current is leading the voltage by 90 degrees. The current is peaking and falling to 0, and in 90 degrees after the current peaks, the voltage peaks. And 90 degrees after the current falls to 0, the voltage falls to 0. And 90 degrees after the current reaches peak negative value, the voltage reaches peak negative value. What we have is vectorially this. That current is going to be on the y-axis. It's happening 90 degrees before the voltage, which is on the x-axis. Okay. There are different ways to represent this. One way is to do it with the two sine waves plotted out, showing that the current is 90 degrees leading the voltage, or showing it vectorially, the current is leading 90 degrees ahead of the voltage. Okay, so they're in phase, they're out of phase. And these two waveforms can be out of phase any degree between 0 and 90. It's funny, they don't use anything greater than 90 degrees. Either the current is leading the voltage by 90 degrees, or it can be lagging the voltage. Or they can be, well, here they're 180 degrees out of phase with each other. Their peaks are exactly opposite. They're falling to 0 at the same time, but their polarities are opposite. So they're 180 degrees out of phase with each other. But usually in an AC waveform, we're some angle between 0 and 90. We'll see that coming up. Will be some degree, and it can also be the voltage leads the current, or the current leads the voltage, but it will be some degree between 0 and 90 degrees. Okay, very good. All right. So two waves with different output voltages are shown in figure 6. Suppose one generator starts its cycle at 90 degrees where the maximum voltage output is produced, wave B. Instead of starting at the point of 0, output wave A. Each of the same waveforms of alternating voltage, but wave B starts the maximum value while wave A starts at 0. So they're 90 degrees out of phase with each other. B is peak, and then 90 degrees later, A is peak. And B is happening before A. Time is flowing from left to right on the x-axis. So B is 90 degrees leading A. The way we read this is it's 12 o'clock before it's 3 o'clock. So B is leading A. And then we go on to phase angle diagrams. The vector VA represents wave A with an angle of 0 degrees. This angle can be considered the plane of the loop in the rotary generator, where it starts with 0 output. These two are in phase. These two waves are in phase. They start at 0, they peak at the same time, they fall to 0, and they reverse polarity at the same time. And here's the vectorial representation of those two waves, B and A, happening at the same time. All right. 1.3.0 non-sinusoidal waveforms. Sine wave is the basic form of AC variations for several reasons. This waveform is produced by a rotary generator. The output is proportional to the angle of rotation. Because they come from a circular motion, any sine wave can be analyzed in angular measure. Angular measure is expressed either as a degree from 0 to 360 degrees or as radians from 0 to 2 pi radians. In many electronic applications, however, other wave shapes are important. Here's a highlight. Any waveform that's not a sine or cosine wave is a non-sinusoidal waveform. Common examples are the square wave, the sawtooth wave. So here's the sawtooth wave. You can see it has both positive and negative aspects of it, but it is not a sine wave. And here's a square wave with positive and negative. You can think of this as two 9-volt batteries wired through a 3-way switch, so that you throw the switch one way and you have a positive voltage, 9 volts, going through a load. And when you switch it the other way, the other one is opposite polarity. You have a negative going through that load, whatever it is. Now, these do not have rotation. They're just values of DC in one polarity and then another polarity. It's a square wave. So that's why down here it says, what's wrong with this picture? Because they've written the degree, the number of degrees here. That's all. There's really nothing wrong with the picture. It's just the degrees. We don't need those. There's no angular motion. There's no degree of rotation. That's all. So here's 1.0.0 section review. If a sine wave is repeated 10 times per half second, its frequency is, well, it's 20 times per second, so it's 20 hertz. I'm just going to go ahead and answer these. To compare a phase angle between two waveforms, both waves must have the same amplitude. Yeah, that's not even one of their answers. The same frequency. They have to happen at the same cycles per second in order to be able to compare them. If you have one wave that's 30 hertz and one that's 45 hertz, you can't say, are they in phase or not in phase? They'll never be in phase. There are two different frequencies. One device that generates a sawtooth waveform is an oscilloscope. All right. Let's go on to the next section. 2.0.0 unknown values in an AC circuit. Determine unknown values in AC circuits. Find unknown values in purely resistive AC circuits. Find unknown values in inductive AC circuits. Find unknown values in capacitive AC circuits. Find unknown values in combination circuits. So, an AC circuit has an AC voltage source. Note the circular symbol with the sine wave inside of it. It's used as for any source of sine wave alternating voltage. This voltage connected across an external load resistance produces an alternating current of the same waveform frequency and phase as the applied voltage. So if you're going through a purely resistive load, this voltage is going to create a current that is in phase with that voltage. It's linear, they call it. So according to Ohm's law, current equals the voltage divided by the resistance. We have 120 volts divided by 10 ohms. We have have 12 amps flowing through that circuit. 2.1.0, purely resistive AC circuits. Here's a highlight. In an AC circuit with only resistance, the current variations are in phase with the applied voltage as shown in figure 9. This in-phase relationship between voltage and current means that an AC circuit of this type can be analyzed using the same methods as DC circuits, since there's no phase angle to consider. So here's a highlight. It says in purely resistive AC circuits, the voltage, current, and resistance are related by Ohm's law because the voltage and current are in phase. The equation can be rearranged to solve for the desired values. E equals I times R and R equals E divided by I. Unless otherwise noted, the calculations in AC circuits are generally in root mean square values. For example, in figure 9, the 120 volt applied across the 10 ohm resistance, RL, produces a root mean square current of 12 amps. This is determined by as follows: I equals E divided by R, 120 over 10, 12 amps. Since the circuit's purely resistive, the current and voltage are in phase and are directly proportional. Because of this, you can use Ohm's law for voltage, E equals I times R, to find the true power of a purely resistive circuit. So we could do E times I, or E squared divided by R, or I squared times R. Because power is the product of the current and the voltage as shown in Ohm's law, P equals I times E. The true power of the circuit, also known as the root mean square power dissipation, can be found by substituting the equation for voltage E in place of its variable. So it says P equals I times E, or P equals I times R, or I squared times R. Applying this formula to the example above, the true power is determined as follows. True power is I squared times R. And again, that I is going to be root mean squared. 12 amps squared, 144 times 10 ohms, 1,440 watts of true power. Inductive AC circuits. This is a highlight. It says the characteristic of an electrical circuit that opposes the change of current flow is called inductance. Inductance is the creation of a voltage due to a current that changes over time. Also, the resulting opposition to current change, which causes the current changes to lag behind the voltage changes. The unit of measure for inductance is the Henry. I always describe inductance as a circuit's ability to store a magnetic field. The inductance is a circuit's ability to store a magnetic field. Capacitance is a circuit's ability to store an electrostatic charge. So it'll actually charge between two plates a difference of potential or a voltage. It is static. If you put it in an AC waveform, then it isn't static, but ever changing. But inductors oppose a change in current. Capacitors oppose a change in voltage. Okay. So it says in DC circuits, a change must be initiated in the circuit to cause inductance. The current must change to provide motion of the flux. A steady DC of 10 amps cannot produce any induced voltage as long as the current value is constant. A current of 1 amp changing to 2 amps does induce voltage. Also, the faster the current changes, the higher the induced voltage becomes. This is because when the flux moves at a higher speed, it can induce more voltage. So here's a highlight. It says, however, in an AC circuit, the current is continuously changing and producing induced voltage. Lower frequencies of AC require more inductance to produce the same amount of induced voltage as a higher frequency current. The current can have any waveform as long as the amplitude is changing. Here's another highlight. It says the ability of a conductor to induce voltage into itself when the current changes is referred to as self-inductance. Magnetic field induced in the conductor carrying the current. Factors affecting inductance. An inductor can be a coil of wire wound on a core of metal or paper, or it may be self-supporting. It They consist of turns of wire placed side by side to form a layer of wire over the core or coil form. The inductance of a coil or inductor depends on the physical construction. Some of the factors affecting inductance are the number of turns. The greater the number of turns, the greater the inductance. The coil diameter. The inductance increases directly as the cross-sectional area of the coil increases. The length of the core. When the length of the core is decreased, the turn spacing is decreased, increasing the inductance of the coil. And the coil material. Coils wound on a magnetic core produce a stronger magnetic field than those with non-magnetic cores, giving them higher values of inductance. All right. So, few turns. If you have more turns, you have a higher inductance. If you have a small coil diameter, if you put a larger coil diameter, you have more inductance. The core length, if you make it shorter, the coils are going to be closer together, and you'll have a higher inductance. And the core material, if you have a magnetic core made of iron, then you're going to have a higher inductance. Voltage and current in an inductive AC circuit. All right. Let's go back to the 3D BB. I have to draw this out for you. I want to try to explain this to you so that we understand. We're going to talk about Eli the Iceman. If you've read ahead in the book, then you've read Eli the Iceman. And let's talk about it. So here we have a wire, and we wrap it into a coil, and that coil is an electromagnet. Basically, it's an inductor. And as we put current through this coil of wire, it has an inductance. When you have a steady state, they were saying when you have DC voltage and current, the inductance is going to level off. Let me see if I can do this. Here's a battery, and that battery is going through a resistor, and we're going to draw the voltage and current. Let's see here. So I'm just going to say that it has 12 volts, and it has 2 ohms of resistance. Nope, I'm sorry, I meant to say 6 ohms. It's got 6 ohms of resistance. So here's 6 ohms of resistance. And if you're real quick, you're saying 12 volts divided by 6 ohms equals 2 amps. You're absolutely right. There's 2 amps flowing in the circuit when we close the switch. Let me put a switch in here. I don't have a switch. There, so now we have a switch. So when we close the switch, we'll have 2 amps flowing. Well, that 2 amps, as soon as we close the switch, it's going to climb to 2 amps, and it's going to stay at 2 amps. When we open the switch, it's going to fall to 0. That's the current flow in this circuit. I want to draw the same circuit, only this time I'm going to use AC instead of a battery. And instead of a resistor, I'm going to use a coil of wire. I'm going to use an inductor. So, well, I'm ahead of myself. I'm going to put a battery. Excuse me. I am going to put a battery. This is the same kind of battery as this circuit, so it's 12 volts. And this inductor has 6 ohms of what we call inductive reactance. So using Ohm's law, when we close the switch, we're going to have 2 amps flowing in that circuit. But that 2 amps isn't going to look like this. That 2 amps is going to climb up to 2 amps. And then when it gets to a point where the 2 amps is steady, the inductor will not be opposing a change in current because the current is steady. And theoretically, when we open the switch, this current is going to fall back to 0. And it's going to take a minute for it to fall to 0. That's because this inductor opposes a change in current. When the current is trying to increase, the inductor is fighting that change, and it gradually gets up to peak, it gets up to the 2 amps, and then the inductor is happy, it stops opposing anything, there's your 2 amps flowing. When you open the switch, the magnetic field collapses, and I know this is just in theory because right now we don't have a closed circuit. If I did have an extra wire on here with a resistor, I just didn't want to go into all of that, but let's put a resistor, and I'm trying to do it with a dotted line saying that it's just imaginary. But there's our imaginary resistor. When we open the switch and the magnetic field collapses around this inductor, the current doesn't just stop. The current will slow down. It'll decay over time. And the time it takes that inductor to either fully charge or fully discharge is 5 time constants. Here I go again with drawing my crooked lines. I don't know why this isn't working for me today. There we go. So I'm going to do 1, 2, 3, 4, 5. And we're trying to get to 2 amps. Well, not to confuse the issue, I'm just going to call this 100% instead of 2 amps. And after 1 time constant, I'm going to get to 63.2% of maximum, of fully charged. And that leaves me, if I took 100 and subtracted 63.2, I would get, 36.8, right? Yeah, 36.8. So if I take my calculator, I know this is convoluted, but just stay with me here. If I take 36.8, which is what we have left, 36.8 times 0.632, I'm going to get an additional 23.25% added on to that. 23.25%. So 23.25% is going to get me to 0.5. Let's see here, let me write this down. 0.5. And 3 and 3 is 6, and 6 and 2. I get to 86.5% in the second time constant. I'm now at 86.5%. Because it was 63.2% of what was left. Now, if I subtract that, I have 13.5. Is that correct? I think so. 13.5% left. And I will take, I'm going to take 63.2% of that 13.5. Every time constant, that inductor can charge to 63.2% times 0.632. Oh, stop that. Okay. 13.5 divided or multiplied times 0.632 equals 8.5. So I'm going to add 8.5 to this, and I'm going to get 95. 95. So here, after 3 time constants, I'm at 95%. And after 4 time constants, I'm going to be at 98.2%, I believe. Okay. After 5 time constants, we're going to be at 99.3%, and that's close enough to 100 that we just go, okay, we're done. So here's time constant 1, time constant 2, time constant 3, time constant 4, and time constant 5. 5 time constants will get us to what we call 100%. It's not, it's 99.3%. Okay. Same with discharging. The first time constant will discharge 63.2%. And the next time constant, we will discharge another, I think it was 23%. And then the next time constant will discharge another 8.5%. The next one will discharge another 3%. And then we'll discharge this last, and we'll get right down to 0. Well, here's the funny thing about it. You can never fully charge nor discharge a capacitor or an inductor because you're always getting 63.2% of what's left. So it just keeps going on ad infinitum. You get 63.2% plus 63.2% of what was left plus 63.2% of what was left. And you keep getting closer and closer and closer to 100%, but you never quite get there. Okay, all right, so voltage and current in an inductive AC circuit. The self-induced voltage across an inductance L is produced by a change in current with respect to time. This delta just means change in current divided by change in time. Okay. This formula provides the voltage in terms of how much magnetic flux is cut per second. The magnetic flux associated with the current varies in the same as the current. This formula gives the same result for calculating induced voltage. Remember that the induced voltage across the coil is the result of inducing electrons to move in the conductor. So there is also an induced current. All right. It says, for example, what's the self-induced voltage VL across a 4 Henry inductance produced by a current change of 12 amps? So 4 Henrys times 12 amps divided by 1 second. That's 4 times 12 equals 48 volts. We end up with 48 volts. Here's a second example. The current through a 200 microhenry inductor changes from 0 to 200 milliamps in 2 microseconds. So after they do their math, prefix micro means 1/1,000,000th. So microhenry is equal to 1/1,000,000th of a henry. So they're doing the math here. They're doing 200 times 10 to the negative 6 times 200 times 10 to the negative third divided by 2 times 10 to the negative 6th. And basically, they end up with 20 volts. So if they were talking about milliamps, and now all of a sudden they have a voltage drop of 20 volts, they can have literally thousands of amps. They can burn this thing up if it's a tiny little inductor. They can burn it up. The overall effect that the current is out of phase and lags the applied voltage by 90 degrees. So we're going to talk about Eli the Iceman. All right, I'm going to draw this on the board. As a result, the current will begin to flow in direction opposite to how it approaches 0. All right, here's Eli the Iceman. This can easily be remembered using the phrase Eli the Iceman. It's a mnemonic, and this says in an inductive circuit, the voltage leads the current by 90 degrees. And in a capacitive circuit, the current leads the voltage by 90 degrees. Remember, L is for inductance. L is for inductance. All right, let's see what we can see. So, oops, wrong color. Let's do this here. Bear with me. I'm going to put an inductor here in this circuit. And remember, that inductor opposes a change in current. So I'm going to draw this voltage. Yeah, it's a series circuit. Oh well, I'm gonna draw the voltage at 0. It shouldn't be, because it's a series circuit, so the current should be the same everywhere. So the current should be on the x-axis. The current should be in phase. But for now, I'm just going to draw this voltage from the source, and whatever it is, we can say it's 12 volts. It doesn't matter what it is. We'll say it's 12 volts. We'll say this is 6 ohms. It doesn't really matter. 6 ohms of inductive reactance. What happens is, as this voltage rises to peak, it's increasing. This inductor is opposing a change in current. It's actually pushing current in this circuit in the opposite polarity as the voltage, till such point that the voltage levels out at the peak. When it gets to that peak, 12 volts, the inductor's happy because the voltage is neither rising nor falling, so it stops producing that current in the opposite direction. Now the voltage starts to fall from 12 volts down to 0 volts. And the inductor doesn't like that. It opposes a change in current, so it's actually going to aid the circuit by trying to put current back into the circuit. We'll say that the negative is on top and the positive is on the bottom for the first half amplitude, and that's why we're going clockwise. So it was opposing it, it was actually putting it counterclockwise. Now that the voltage is decreasing, and we always flow from negative to positive external of the source, now that the voltage is decreasing, this inductor opposes a change in current by actually pushing current in the same polarity as the voltage, until such point as the voltage is changing direction. That is the maximum amount of change per time right at this point, and it's producing the maximum amount of current in that polarity. Now the same as this first half of the amplitude, this amplitude is rising to peak negative value, and because of that, the inductor is opposing a change in current by producing a current in the opposite polarity. So the current is actually in the positive amplitude when the voltage is in the negative amplitude. Until such point as this voltage levels out, it's neither rising nor falling, so the inductor's happy and it stops producing current. When this voltage starts to fall back to 0, the inductor tries to oppose that change in current by producing current in the same polarity until its maximum. At this point, the voltage is changing its value at the maximum rate of speed, so the inductor is producing the maximum amount of current. And then as this rises to the positive peak, it does the same thing again. It's producing current in the opposite polarity until such point as that voltage levels off, and then the inductor's happy, so it stops. So look what's happening. Here's my current. Here's my voltage. My voltage is leading my current in an inductive circuit. Eli. Voltage leads current in an inductive circuit. Later on, we will talk about capacitance, and we'll see that in a capacitive circuit, the current leads the voltage by 90 degrees. In an inductive circuit, the voltage leads the current. In a capacitive circuit, the current leads the voltage. That's Eli the Iceman. Okay, let's go back to our book. So this can be easily remembered using the phrase Eli the Iceman. Eli represents voltage, inductance L, and current I. In an inductor, the voltage leads the current just as the letter E leads or comes before the letter I. The word ice will be explained in section 2.3.4. Inductive reactance. The opposing force that an inductor presents to the flow of AC cannot be called resistance because it's not the result of friction within a conductor. So it is not resistance, it is reactance. The name given to this force is inductive reactance. Reactance is an opposition to current flow. The opposition to AC due to the capacitance is X sub C, and or inductance is X sub L. We read the subscript first. Capacitive reactance, the X is reactance, or inductive reactance, the L is inductive. Inductance. So inductive reactance, capacitive reactance. Remember that the induced voltage in a conductor is proportional to the rate at which the magnetic lines of force cut the conductor. The greater the rate, or the higher the frequency, the greater the counter electromotive force. So also the induced voltage increases with an increase of inductance. The more turns, the greater the counter electromotive force. Here's a highlight. It says reactance then increases with an increase of frequency and inductance. So here is our formula. Hexabel, inductive reactance, equals 2 times pi times the frequency times the inductance in henries. The inductance in henries. Hexabel equals 2 pi times the frequency times the henries. Okay. All right. We can draw a magic football. The reason I call it a magic football, I had a student once, I said I called it a magic circle, and he said, no, Mr. Young, that's a magic football. Here's my magic football. And it's just like the Ohm's law wheel. I'm going to put Hexabel on the top. And I'm going to put 2 pi. And the inductance, L. And I'm going to use the red for frequency. So you cover the unknown. Let's see here. What do I have? Let me have a circle. And let me fill it in. How do I fill this in? I forget how to make it solid. Fill color. Oh, it doesn't matter. I'll just make it yellow. There. All right. Why did that not work? There we go. All right. So we'll cover the unknown. If we want to know what Hexabel equals, it equals 2 times pi times the frequency times the inductance. If we want to know what the inductance is, we can use the formula Hexabel divided by 2 pi times the frequency, and that'll tell us the inductance. If we don't know what the frequency is, we can find it by doing Hexabel divided by 2 times pi times the inductance. That's the frequency. Okay. So just like the Ohm's law wheel, this inductance football, you can cover the unknown. All right, very good. Let's see here, where Hexabel is the inductive reactance, 2 pi is 6.28. The frequency is the frequency of the AC, usually 60 hertz, but they're going to change it on us when we're doing the math. And L is inductance. For example, if the frequency is 60 hertz and the inductance is 20 henries, find the Hexabel. So it's 2 times pi times 60 times 20. We get 7,536 ohms of inductive reactance. That's opposition to current flow. It's not resistance. It's opposition to current flow. Once calculated, the value of Hexabel is used like resistance in a form of Ohm's law. Yes and no. So here's a highlight. It says the energy required to build up the field in the inductor is returned to the circuit when the field collapses. And here's my Eli and Eli the Iceman. Remembering the phrase Eli as an Eli the Iceman is an easy way to remember the phase relationships that always exist between voltage and current in an inductive circuit. An inductive circuit is a circuit that has more inductive reactance than capacitive reactance. The L in Eli indicates inductance. E is the voltage, the I is the current. All right, very good. I'm going to stop here and start a new video on capacitive reactance.